let's review the types of shear or triaxial tests we can carry out in the laboratory. The simplest is what is called unconfined compression test. The soil sample, a cylindrical one, usually about 1.5 inches in diameter. That's about 37.5 millimeters by 75 millimeters. You just put it in. This you can do only with fine-grained soil, because coarse-grained soil will not retain the cylindrical shape. Only when you have fine-grained soil and some water, you can have this. You apply the normal stress, get the stress strain curve, and carry out the test. And because there are no confining stresses, you call it as unconfined compression test. The more sophisticated and very popular test is called triaxial compression test. Look at this. I have the soil sample, exactly the same as before, 1.5 inches in diameter. It's enclosed in a rubber membrane. Okay, then you put in a top cap, and you are keeping a porous stone, and maybe you put a filter paper, etc. And you put the rubber membrane. You put some O-rings so that the rubber perspex sheet or the membrane is tightly held and no water can escape into this. Okay, then this is a triaxial cell. We assemble, put it on top. It has a plunger so that when I apply a load on top, I can apply to the top. And again, you seal it. The chamber, the triaxial cell, is put on the pedestal, base 1, and then you put some screws so that this is tightly joined together. Look at the contacts. I have a water connection so that when I pump in water, I can fill up this cell and increase the pressure so that the soil sample gets a 3-dimensional or equal all-round pressure. You have a connection from the bottom of the sample through the porous stone so that water from the sample can drain out, or if you close it, I can make it undrained test. And here are the usual screws, etc. And when you are filling with water, you want to remove the air, so you have a release valve here. The water is pumped in here, and the water which is inside the cell goes out. Okay, and all these are very well sealed. Unless you have very good sealing, the test is never good. And this drainage line is connected, this outlet is either connected to a drainage pipe or you have to have a pore pressure connection. And this is a must and a good test in all the cases. So again, the same in all much more detailed one. So this plunger applies axial load. See the soil sample, flexible membrane, equal all-round pressure or confining pressure. This is the drainage line. You have a valve. If you open the valve, the water from inside can go out, or if you close it, it will become undrained. You need a porous stone so that the soil cannot go out, only the water can go out here. So the stage in which we do is, I take the sample from the field. Initially, there is no vertical stress, no horizontal stress. Maybe there is some residual pore pressure, so which means initially there is a negative pore pressure, because of which you may have some effective stresses. Then you are applying confining pressure, and you are allowing drainage, which means pore pressure is 0. So now effective stresses are equal to the total stresses. In the second stage, you are applying a deviatoric stress, and again no pore pressure. Pore pressure is allowed, drainage, so you will get the final state of stress. This is called the consolidated drain test. You are allowing water, so pore pressure is always 0 under any applied stress. This is consolidated undrained test. Initially again you have no vertical stress, no horizontal stress, some pore pressure, so you may have negative effective stress. Now when you apply the confining pressure, chamber pressure, you are allowing drainage. So the soil sample has got consolidated. Now we are applying the deviatoric stress, and now you are closing, and so you will have pore pressure. And when you want to calculate the final state, This is the confining pressure plus the deviatoric stress, and you deduct the port pressure. And the port pressure also affects the confining pressure, so the lateral confining stress decreases in the CU test. In the undrained test, initial state is same as before. When you apply the all-round pressure, you are closing, so you will have port pressure. And it's a function of the parameter B, which is equal to 1, so you will have very high port pressure. And if B is equal to 1, you can see that 1 minus 1 is 0. No matter how much pressure you apply, the effective stress will not increase. That means the soil will be in the same state as it was before, no matter what we do. So when I apply the deviatoric stress, it is independent of the confining stress. For a saturated sample, there is no way you can find any strength as a function of the confining stress. So if I apply confining pressure, the P increases. Sigma 1 minus sigma 3 is 0, but when you apply the deviatoric stress, you get the stress path in this direction. The volumetric strain, even if it is undrained, please remember, I can have a specimen of this kind. It can, under same constant volume, the length can decrease, but the diameter can increase. So this is how we try to analyze this. So you can see here again, P is sigma 1 plus sigma 3 by 2. Q is sigma 1 minus sigma 3 by 2. So initially, Q is 0. When you apply the deviatoric stress, you are increasing P and you are also increasing Q. So you find that it's a 45-degree line. Both P and Q are increasing. Please remember here, sigma 1 minus sigma 3 by 2. So port pressure gets cancelled. It's exactly the same. So this is how the soil specimen under triaxial conditions. Why do we apply the confining stress? Because the soil inside the ground is subjected to all-round pressure. And also, when you confine it higher, you are reducing the air voids, and so you are increasing the degree of saturation, and the soil will become closer to reality. Also, there may be some fissures. When I'm taking a sample out of the ground, small cracks may open up. So when I confine it and apply sigma 3, I'm closing the fissures again. No drainage, then the soil will have to take the applied stress. All of it will go into port pressure. So you will develop port pressure here. In the undrained test, you will have port pressure. In both cases, when you apply sigma 3, confining pressure, you will have delta U1. And when you apply the deviatoric stress, you will have delta U2. And finally, it doesn't matter what is the initial state. The final state is exactly the same as before because the soil is saturated. So what you get is an undrained strength of the sample. This may be the real envelope because you have only one circle. No matter what is the confining stress, you get only one circle. So we end up getting a horizontal line which is saying that soil is in an undrained state, and this is called CU undrained strength, and the angle of shearing resistance for U is 0. So this is how any number of tests you may do, the failure envelope will be parallel to the x-axis. This is the stress path because the port pressures will not change the effective stresses. In the CU test, you will find that, as I said earlier, as you increase the port pressure during deviatoric stress, sigma 3 decreases and you will get a failure envelope. Depending on the kind of soil, the effect could be significant. In case of a sensitive soil, the decrease could be very significant. In a less sensitive soil, the port pressures are less and you stop failure here. This is the drain test. Port pressure is always 0. So the failure, if I'm just saying sigma 1 is increasing, it will go vertically. Sigma 3 is increasing in this direction. So when I do 3 tests, I get the failure envelope, and here is our failure envelope. CU test with pore pressure measurement is not a very good one to interpret, but with pore pressure you can interpret it better. You can do with isotropic consolidation, which means sigma 3 is the same. We can also have pressure so that K0 condition can be replaced. That is called anisotropic consolidation. And what you will find is you can determine the effective stress envelope where the friction angle is high, whereas if I plot with total stresses, I get CCU and phi CU if you measure. And here is the other interesting thing. As I said, in case of normally consolidated soils, pore pressure is positive, stress path comes this way. And in case of dense soils, when the pore pressure is negative, you will find when U is decreasing, you get a higher strength.